I'm an engineer because I did my study in civil engineering in Delft. Later on I did my PhD in physics in Utrecht, where I also became a professor part-time. And my present function is Deputy Director of NIOZ, Royal NIOZ.
Who's the director? The Queen?
Yeah, that's the Queen, the Queen of England. Well, that's Carlo Hyde, a Belgian guy. Okay. Thank you. So what I will do, my talk today will be mainly the same talk as I gave roughly a month ago on the vpro Sunday in Utrecht, where they invited a few speakers to give a talk on the research being done in the framework of the whole Beagle experiment. And we as NIOZ were approached roughly 1 year ago by the vpro, and they told us about this marvelous trip, and we found that, of course, a wonderful idea. And because we study the oceans, and because the Clipper is mainly in the oceans, traveling all around the world oceans, a lot of our scientists also joined partly the trip. And I'm here on the last part of the trip. And today I will tell mainly on of course, the studies I'm involved in and why I'm on board during this trip. But I'll also speak a bit on the other studies that are being done at this moment daily. Okay, so I'll focus on ocean currents and the role of the oceans in the climate system, simply because that's my, say, own background, and that's what I study in this area. First of all, I should say that back in the time of Darwin, they really thought that the ocean was something just to travel over or to get seasick, but not interesting at all. Only near the shore where you find some animals, but for the rest, Darwin just used the ship to go from one place on land to another place on land and to do studies on land. And that continued actually quite long. It's only 100 years ago that they took the first serious measurements in the ocean. And it's only, say, 30, 40 years ago that the real ocean research became possible, just because of instrumentation that was developed. But you should keep in mind that the oceans are very important for our whole world, for the whole planet Earth. And that's because of a very simple thing, is that the oceans cover more than 70% of the surface of our planet. So in fact, what we always say, we should not call our planet Earth, but we should call our planet ocean. And well, you see it a bit in different views from the Earth, what you see here, and you see the dots indicated here. Those are the areas where our institute has done research thus far. You see some, say, areas where we do a lot as an institute. Of course, in the North Sea and the North Atlantic Ocean. And we have a spot in this area where we do quite a lot of research. And that's also from the past, I think. We did do and still do quite a lot in the Indonesian waters. And we do that with our vessel, which is the Pelagia. We have this vessel since 20 years. And that's also roughly the time, or maybe 20 years before that this whole ocean research started to grow. And this vessel we use normally to do our studies, and we will meet a similar vessel but a bit bigger in a few days. And that's the American research vessel, which is doing similar things as I'm doing normally in this area. So we really loved the idea to join the Clipper, and we do some research. That's possible on this ship, of course. And you've seen myself maybe taking water samples every morning, and that's being done also by Ruud and all the people from the ship. But when there were NIOZ scientists, they did that daily. And we do that just simply because from many parameters, it may be strange, but we really don't know yet good distributions all over the world oceans. So if there is an opportunity to have a ship and to do these kind of things, we often participate in these kind of things. And there are also a lot of, as we call them, VOS vessels, voluntary observing ships, sailing around who take observations for oceanographers. And what we do here is, what I do now daily is I take water samples and put them in the -80 freezer for determinations later on. And what we will determine later on is the amount of nutrients. Those are the building blocks for the growth of algae, like phosphorus, nitrogen and silicate, viruses, bacteria and plankton. And then we do, I'll show those a bit later, sensor observations from behind the vessel with a CTD, where we measure temperature, salinity, fluorescence and transmission. And that's measured, say, on a second base with sensors. Well, as an example, it might be strange, but viruses, the presence of viruses, that they are there in the ocean, is really only known 10, 15 years or so. And the differences in these viruses, and we know now there are roughly 1 million or more than 1 million viruses per cubic milliliter of seawater. But what they do and how they influence the whole marine ecosystem is really not known. It's only known, well, very fragmentary, and it's not known what different types of viruses are there. And you can imagine that, like on land, that these viruses play an important role in regulating the ecosystem. Like you have, for instance, large fluctuations in, for instance, populations of rabbits on the islands where I live. That has to do with viruses that come up and go down again. And similar things may be present in the ocean, which we do not know at this moment. So I collect these samples, and later on in the institute they will be analyzed, and it will be looked after what type of viruses are there, and I'm quite sure that they will find again new ones, because that's also a big thing in the oceans. If we would trawl a net deep in the deep oceans, and we would do that for a day in the really deep ocean, then it's quite sure that we do find new species. Whereas if you would do that on land, it would be very difficult to find new species. There are a lot of undiscovered species in the oceans. It would be very good, that's what Redmond suggested recently to me, for one day to dry out the complete oceans and then see what's over on the seafloor. And it would be full, because there is a lot which we simply don't see. That's the real problem of the oceans, you could say, that if you look outside, everywhere looks the same and you can only see the surface. But below that there is a lot of, not only currents, but especially there is a lot of life, which we really don't know of anything at all. But that's my subject of being here is also mainly because the ocean is a very important component of our Earth's climate system, so our physical system. And I won't speak about that, but for instance, Bubbo is taking observations for that, is that the ocean also takes up CO2 from the atmosphere. So remember, the oceans are more than 70% of the entire Earth, so what the oceans take up is far more important than what the land surface is doing. But the estimates we have at present are very rough. They could differ a factor of 10 or so if we do more observations. But I won't speak on that. Where I will speak on is the ocean and the ocean currents and their role in redistributing heat around the globe and their importance for our daily climate. We all know that you should keep in mind that the oceans, if you warm up the oceans can really store heat. We know that there are sea climates and land climates. If we live in the Netherlands, for instance, we have a relatively mild climate because we are nearby the sea. And if you are in the middle of the land, you have much more fluctuations, much more heat in the summer and much more cold in the winter. And that's because there is not an ocean nearby. Because the ocean takes up heat in the summer, keeps it, and thereby keeps heat also in the winter time. But that's, say, a local effect, but what the oceans also do is that they bring heat from the tropical areas, so from the equator, towards the poles. And that's very important also for our climate. And I'll show some examples of that, because that's my main subject. And I'll start with this one, because that's very important, and it's also good for the background to know. This is the North Atlantic Ocean. England, the Netherlands. And what we have, I show here the current system, the surface circulation in the North Atlantic Ocean. What you see is that we have in red, a relatively warm current, the North Atlantic current, and that's a branch of the Gulf Stream that brings warm water towards the north, all the way up to Norway. And with our, in general, westerly winds, we get in Europe heat from the ocean. Whereas on the other side of the same ocean, there are, at the surface, circulations from the poles towards the south. So this circulation is relatively cold. So the consequence of this is that Europe is on average some 5 degrees or so warmer than at the same latitude, the same distance from the pole, than what you have in Canada. Over here at the same latitude, Eskimos, Inuits live, whereas here we live. And that's simply because the ocean is in between and because we have this circulation in the ocean. So if this circulation would change, you can imagine that the whole climate in Europe would change. And I'll come back to that later, because that's it's very much under debate at the moment whether the climate change we experience will influence this current system. And there are really wide opinions on this. But again, I'll come back to that later, because that stimulates us also for our research, even over here in the Indian Ocean, which might sound strange, but that's reality. Okay, the fact that the ocean circulation is important, the coupled ocean circulation and the atmospheric circulation is important for climate, and also in a natural situation. That's what we know from El Nino. We all know El Nino. There was also a vpro series on this, a part of the Beagle documentary, and Beagle also showed it. But what we have, El Nino is a natural climate phenomenon with every 5 to 7 years changing ocean currents, which heavily influences the climate on both sides of the Pacific. So you get much more rainfall on one side. On the other side, you have problems with fisheries because there is no food for the fish anymore. Anyway, it has a lot of consequences. But the good thing of this is that 20 years ago, we didn't understand this phenomenon. Now, we understand this phenomenon, and once you understand it, you can predict it. So nowadays, we can predict this phenomenon. So when it occurs, we know roughly half a year ahead, we know that a new El Nino is coming. And the good thing is that we warn for instance, fishermen and farmers, that they know that next season we will have an El Nino phenomenon, so that they can take care of that and they can do different farming as they are used to, or they know that the fisheries will be much worse than the year before. So it really has a lot of economical consequences also. Oh, did I sorry. Anyhow, so the El Nino is 20 years ago. We didn't know how the system works, so we could not predict it, but we do think, we have got reasons for this, that the ocean also plays an important role, for instance, in last winter, that we had a much colder winter than usually in the Netherlands. At present, we don't know how this come, but the key may lie in the oceans, because of this long-term effect of storage of heat and releasing heat again to the atmosphere on longer time scales. For the weather of tomorrow, the oceans don't play a role, but for the weather in a month, or in a year, or in 10 years, the oceans do play a very big role. Well, before I continue with, say, speaking more on the role of the oceans in the climate system, I'd like to show first some general knowledge we all know about the ocean and about the ocean currents, because that has been known for centuries, and many people think, okay, we know everything about the oceans. And that's, for instance, we know a lot. We know from the old seamen who went like in the Columbus time and the VOC time, when they went with the ships, they measured the currents also with the ships. And from that we know, for instance, that in the Atlantic Ocean, on average, there is this gyre, and that has been known for long, still the same. And that knowledge is still, say, the basic knowledge, what you also find on the nautical charts here, what the officers use and the captain uses. And this is a world map, what you find in the atlases, in the Bos Atlas, for instance. And there you see all these gyres, what is spoken about also in regard to the plastic. In all the oceans you've got these relatively large-scale gyres circulating around. Southern Ocean, this one in the Indian Ocean, this one in South Atlantic, this one in the North Atlantic, and this one in the Pacific. You should see this as an average circulation. It's the same as saying in the Netherlands that we have a wind southwesterly 3 by 4, because that's what we do have on average, on a yearly average. But the daily wind can differ enormously from the average. But this is the picture we have in mind, and this is also what is, for instance, on the charts the navigation people here use. And that has to do, this is driven by the large-scale wind field over the oceans, the Passaatwinden, which drive such a current system. And it's good to remember that this knowledge, these currents, are also known for, say, more than 100 years or so, and it's all because of ships like this. They take a position every day, and they then say, okay, we have a log in the water, we know how fast we go, we know which direction we go, and we should end up here next day. And then they do a new measurement, and then they didn't go here, but they went there. And the difference must be due to the current. And that's what they noted, and from all these observations they came up with this general circulation scheme. So that's known for centuries, you could say. So this is the surface circulation. And in the time of Darwin and even 100 years more, we all thought that this was, say, the circulation in the ocean. By the way, you can also see it still with modern measurements. This gives the distribution, the temperature, sea surface temperature in the oceans. And you can also see the effect of this big gyre. For instance, in the South Atlantic, you see this is the gyre. This gyre brings then relatively cold water up north and relatively warm water from the equator to the south. Similarly, in the Indian Ocean, the relatively warm water is brought along this continent. And you'll be amazed in Cape Town if you come from the Indian Ocean, the water is 5 to 10 degrees warmer than on the other side of the peninsula nearby Cape Town, where the water comes from the south, where it's much colder. So this gives, that's the effect of the ocean gyre circulation. Well, it's only, say, 50 years ago or so that people realized that there is not only a surface circulation, which is driven by the wind. And till then, everybody thought that was all. I mean, that was all of the circulation in the ocean. But then people did, and I show here a cross-section through the oceans from the North Pole to the South Pole. So it's roughly 5 kilometers deep, 5,000 meters deep. And here I show temperature, and here I show salinity. But just look at temperature. So 5 kilometers deep, this is the equator. So till then, everybody thought at the equator, where it's always warm, always 30 or 40 degrees, that the water would be 30 or 20 to 30 degrees all over the water column, till great depth. Why not? I mean, it's always warm over there. And then they took measurements just by lowering a bottle deeper than 200 meters or so, and then they measured water which is 5 degrees at the equator. And if you go deeper, even up to almost 0 degrees. And it appeared, they did the first whole measurements in the 30s of the last century, that the warm surface water is a sort of a pancake only on very cold water. So the whole ocean is very cold, apart from this part. The rest is all cold water. The big question, of course, was then, how come? How come that the whole ocean is cold if it's always warm over there? Well, and then they started to realize that this cold water should come from somewhere. Otherwise, it would be warm. So it should come from the poles. And then they took also salinity measurements. And salinity is also an indicator. If you measure somewhere a salinity value and you measure the same somewhere else, then the water should come from there. Anyhow, then people realized that there must be a deep sea circulation bringing cold water from the poles into the deep seas, from this side and from that side. Well, and then they did more and more measurements, of course, and nowadays picture we have is that apart from this surface circulation, we also have a sort of three-dimensional circulation in the world oceans, and we call this the overturning circulation. Let me explain that, because this is a very important part in the whole story about what do the ocean currents do with respect to climate change, etc. What you see here is in red is the surface circulation that connects all oceans. Okay, so it comes from into this South Atlantic Ocean. This is very schematic, of course. Goes into the North Atlantic Ocean, and this is the branch which I indicated before as the North Atlantic Current, which is very important for the climate in Europe. And then it sinks to the bottom, so it's getting colder, it sinks to the bottom, and then it returns as a deep sea current along the bottom back in the North Atlantic Ocean. And then it comes up in the other oceans again. But this whole system connects all the oceans. So you can see rather immediately that if, for instance, something changes here or here, that it may influence the whole circulation even up to the North Atlantic. And nowadays, if we do that in computer models, you do see these changes also. There is now a big debate whether if something changes here, for instance, in the end can influence it over here. Another big issue, where they even made a Hollywood film about, is that this sinking, so this is driven by density differences. What it means is that this water becomes colder, and because it gets colder and salt and is salty, it sinks to the bottom. But if this would not get salt enough anymore, and that could be the case if the Greenland ice cap melts, so we get global warming, the Greenland ice cap melts, then you get a lot of fresh water here. And fresh water is lighter than salty water, and that could mean that there would be no more sinking of water over here. And if there is no water sinking, then you don't need water to flow over there. So that would mean that this current would stop. If this current would stop, then there would be no more heat brought towards this region, which would mean that we would have a colder Western Europe. So the scenario then is we have global warming, by which the ice caps melt, which in turn gives a regional cooling. Well, this is, as they called it in the IPCC reports, they also mention this possibility, and then they say, okay, this is, well, the chances are not high, but low chance, high impact scenario. It could be that this could be an effect of the global warming. But at this moment we simply do not know, and the reason behind that is that we don't know the system enough, like we would like to know, like El Nino, to be sure on these kind of effects. Well, anyhow, this is a big issue in the say the global ocean circulation research, and there have been developed big global programs, research programs on this issue, and we contribute to that as the Netherlands in different areas of the world where we do long-term research on variability in the ocean currents. Well, I spoke on this before, that often nowadays in the newspapers you see similar pictures with this type of diagrams and saying, okay, if this current stops, then we get colder climate in Europe. And even Hollywood made the film on this. Well, so what we have, as in the Netherlands, we have long-term observations near Greenland. We had in Indonesia, in the Indonesian through flow. And why I'm here now is that we are also very active here in the Mozambique Channel, measuring the ocean currents and year-to-year variability. And the other dots are all dots from different countries. And we all bring these data together towards one big data center to further analyze the data and to look whether variability in one part has to do with variability in another part. And for instance, this whole data set, or all these moorings, has been put a lot of money into it, and that's because these monitor the El Nino evolution, because we know that predictions of El Nino saves a lot of money, and that's why a lot of money has gone into this system. And these are not there yet, but there seems to be a similar climate oscillation in this part of the world, although we are not sure yet, but we are studying that at this moment. Well, what I do in practice, if I go over here, I go there with a research vessel to that area, and you see a cross-section of this over here. It's roughly 3,000 meters deep. This is the one side. This is the Madagascar side. This is the African side. and we put on the seafloor big weights, and we couple to that long cables. You see them here, and with on top these floats, and maybe a bit like a kite. They are in the water, and on these cables we couple current meters, temperature sensors, salinity sensors. Those are all these kind of dots, and then we measure on a hourly basis all these variables, and we go there every 1.5 to 2 years, and then we take out all these moorings, as we call them. We read out the data, and we service them, and we put them back into the ocean again. We started with this in 2000, and thus far we have got funding to continue that till 2012. And we will go, by the way, we will visit the Americans who are deploying similar moorings downstream of where we are, and we combine those observations and study changes here, whether they affect changes over there. But that's similar work. Okay, what we did find thus far, and now I come back to more to the say the actual ocean currents. What we did find is that in this area is indeed also in a quantitative sense an important branch of the global ocean overturning circulation. But thus far it was always thought that there was a continuous current here along the coast. We found that it's in fact a series of circulating eddies moving down, and that these eddies influence in the end also the exchange of Indian Ocean water into the Atlantic. And this is of importance because these contain relatively much salt, which is again of importance for this overturning circulation. And what we are now heavily studying on is on the year-to-year variability, whether we can couple that to other larger scale climate phenomena in this region. And we do that with, by the way, with physical oceanographers like myself, and modeling people who try to model all these phenomena in mathematical models, and geological people who look also into the past, whether you can see whether in the past there have been changes in this ocean circulation. Okay, this was about the effect of ocean circulation on the climate, and now I go to more what we discovered the last 10 years or so, and I think Wubbo has also seen that from above, is that thus far we always thought that the circulation was relatively regular in the oceans. And since the satellites came, we saw that in fact, you see this immediately from these pictures. For instance, this is the temperature near California. You see all kind of features in there. It doesn't look regular at all. Similarly, chlorophyll near the coast of Australia. All kind of circulations. Similarly, here, light reflection by plankton. It's not that regular at all. And what we discovered the last 10 years is that also by going out then and measuring the currents in the ocean, is that the ocean is full of these eddies, as we call them. So those are circulating phenomena in the oceans. And we have that also here in this area. This is Madagascar, this is South Africa, this is somewhere where we are now. And we can measure from the satellites the height of the oceans. And what appears from these measurements is that the ocean, there are sort of hills and small mountains, hills and valleys in the ocean, like you have high and low pressure in the air. And like you have high and low pressure in the air where the wind is circulating around, there are also currents, ocean currents, circulating around these high and low pressure systems in the oceans. And till say roughly 8 years ago or 10 years ago, we did see these pictures, but the interpretation was not clear. And still, this is highly subject of study. But what we discovered, for instance, in this area, because we do these measurements, that indeed these kind of features are very strong circulating eddies in the ocean. And that they live in the atmosphere, these high pressure systems live only for 1 week or so mostly, and these kind of things can live up to 1 year. They travel through the oceans for 1 year or so. And on the boundaries of the oceans, you find often you find a lot of life, birds, what have you. So that the oceans are not so, by far not so uniform as what we all think if you look outside, because then you see always the same. And if you look at the atlases, then you see the currents which are very regular. But there is also a sort of ocean weather, as we call it. Well, and you can derive from these things, you can also sort of guess the ocean currents. This is from, well, specific day in November. And then you can see that there are these highs in the oceans around which the currents circulate. But these things move through the oceans.
So it does have something to do with the height of the depth of the Earth,
No.
or nothing?
No, it has to do with if you, I'll come back to that later. Yeah, I'll come back to that later, I'll show you later. Because I do have, so anyhow, there is a lot of variability in the oceans. And just to show you, I got some data from Ronald from the CTD behind our ship, simply showing from last Sunday data from the CTD. We were all on board, nobody saw any difference during the day in the water, nor did I. But if you look at the data, on last Sunday, the temperature in the water rose more than 3 degrees during the day. So it was 25, it came up to 28 in a relatively short time. If you look at we have a sort of chlorophyll sensor, so measuring the amount of plankton, you could say, in the ocean. That was relatively high, 4 to 5 times higher than here in this colder water. So apparently there was an enormous jump in the amount of phytoplankton. And today I looked, this was then, this is Madagascar, this was the course the clipper had. And during that day we came from, say, this area against the currents, but where the currents came from the south. We entered the area near the coast, but you don't see the average current, but we entered the area where the currents are this way. So if you go back, we came from a relatively cold area into the warmer area where the currents came from the equator. And that's really also a really different regime in the life in the oceans. Well, that's all happens outside, we don't see anything of it. We would see it if it would be in the air, but we don't see it in the ocean. But it is over there. And now I come back to your question. These eddies, this is the whole Indian Ocean. And we know that there is a strong current along this coast. And if those currents flow into the open water, then they always tend to go into circular motion. It's a bit like if the currents got very strong, if you pull through the water, then it's not a straight line of motion, but will be all kind of swirling motions. And that's a bit similar in the ocean. And they organize then in large scale eddies. It's the same over here. Here we have a strong coastal current, and then the coast of Africa goes this way. The current cannot follow that. It comes in the open area, so to say, and then it organizes itself into these large-scale eddying motions. And they form sort of the weather of the ocean.
How deep are they?
Until 1,500 meters or so. Yeah, very deep. Well, and then I took some pictures from the internet also for the coming days, for instance, satellite observations. You can also look at chlorophyll and sea surface temperature. This is sea surface temperature from last Monday, just to show you it's a very nice phenomenon what we see. We are here, roughly. This is South Africa, and this is temperature. So this is the famous Agulhas current, where we've got these freak waves. And normally, this Agulhas current follows the coast. What you see here in this picture is that this current bends away from the coast and comes back. See that? And the difference in temperature is, well, red is something like 26. Bluish is 20 or green. So there's an enormous difference between the temperature over here and here. And here we have strong currents, and here we don't have currents. Normally, also with respect to navigation, you want to avoid this area if there are freak wave conditions. And then you avoid this, and you go out that way. If you don't know this, that it is now this way, then you would maybe go there, but you are still in the area of the freak waves. Why does this come? And it goes too far, but I'll show that maybe later. That's because one of those eddies, if that comes down, circulating, then it pulls out the Agulhas current. So there is something circulating here, it pulls out the current before it reaches back. And in the end, this pulse will move into the Indian Ocean. And that also has an enormous effect on plankton and on life, because this picture also from the 12th of April for the same area, you see this is chlorophyll. So it's a complete desert over here, nothing, and the colors are where the life is, so where plankton is. And they are extremely large outside of this warm current, but you see also here the same. So inside in the cold waters there's life, there is a lot of plankton, and outside you don't see anything. Nowadays fishermen, by the way, they use already these satellite pictures to go to the areas where the fish is.
Herman, does it mean that the blue part doesn't contain any plankton at all?
Wow. Compared to. There is a bit, but not much. You do see some streakiness sometimes. Spots. These are sort of hot spots. Can be somewhere in the ocean. If there is something like an upwelling, it all has to do with currents, which bring up nutrient-rich waters. Okay. What I hope you learned from this is that oceans can be interesting and that they are very variable. So it's not so uniform as we think. And that the eddies and currents in the ocean are very similar to high and low pressure systems in the air and wind in the atmosphere. And we are starting at the moment to learn more on these and to understand these. And I expect that in 10, 15 years or so, ocean current predictions will be similar to weather predictions. So that standard people on the boat get also ocean current predictions for their routing. Because it does differ a lot if you've got two knots with you or against you. If the speed of your vessel, this vessel, now we sail 6 knots or so. If you would have two currents with you, we would go 8 knots. If you have two currents against you, you go 4 knots. So it really doubles the time or doubles your speed. This is a nice picture I took from tropical cyclone Huda when I was in the area in 2000. And I'm convinced that similar, like tropical cyclones, are also present in the ocean, only we don't see them. We see these tropical cyclones. The fish know from the tropical cyclones in the ocean, but we don't know, or we start knowing that. That's about it, I think.
Herman,
Yeah.
you said the flow
Well, yeah.
We are heating up the Earth only for the last, let's say, 50 years, out of which the last 20 years is more serious. What kind of time frame of heating up the ocean do you think will start to play a role?
Yeah, that's a good question. This whole circulation, the overturning, then you speak about time frames of 1,000 years or so. But what we do see, and which I will show later in the North Atlantic, we do see heating up of the, as we call them, the midwaters. So at till 500 to 1,000 meters depth, we do see a heating of the oceans already. In the surface water and in the intermediate waters. Not yet in the deep bottom waters. But if you heat up, so everything that goes down is a bit warmer now, but it will have effects even in 1,000 years from now, because everything is kept in the oceans at that temperature.
Now with the greenhouse gas, we roughly know that about half of the greenhouse gas which we have made is absorbed in the ocean.
Yeah.
Do we have a similar number for the amount of heat, the amount of extra heat which the Earth has received because of the greenhouse gas?
I don't know the exact number. What I do know is that it's in the oceans it's much more than in the air. And that has to do with the heat capacity of air compared to the oceans.
What it also means that it could well be that the effect which we now introduce on the Earth is much larger than we really anticipate or really see, because the oceans are really kind of dampening.
Yeah, I agree. I fully agree with you. So if you would say get rid of the problem in the air, then you still have on the long time scale you have got the problem from the oceans. Yeah. Fully agree.
And if the ocean gets warmer, you showed a picture where you see, you said it's like a desert.
Yeah.
It's so warm. Do you expect these deserts in the ocean to get larger and ocean life to get affected by that?
To be honest, I don't dare to say. What's very important for life in the oceans is that there are regions where there is upwelling. So where the currents bring water from deep. That has to do with the nutrients in there. So the surface water are depleted. It's like the vpro, the documentary we saw recently with the dust. Dust is very important. Why? Because in dust there are elements which are important for the growth of plankton. And similarly, there are elements in the deep sea which are also good for the growth of. So if it affects the overturning circulation, if that on average becomes more or less, but to my knowledge that's not known.
You wouldn't say you have to be careful that the whole ocean becomes
no. Where we should be careful about, and what really a problem is with CO2 is the acidification of the oceans. It's another thing, but so that the calcium will dissolve. That's really a problem for the corals, for instance. But that's other issue. But seems to be very serious at the moment. They can make. Yeah, but by the input of CO2. Simply a chemical reaction. I think all those, apart from the heating, all those other effects with, like also the change of the surface of the land, all those effects could be far more important even than heating as such.
You said when you described the conveyor belt, which is the sinking of cold water and getting up to the element, there is a lot of debate about the question if that will influence the climate in Europe, let's say. Why is there so much debate about that?
Well, no, there's not. If it changes, there's no. If it changes, it will influence the. But the debate is on whether the freshening of the water will be enough to stop the sinking of the water.
I see.
Yeah? That's the debate.
it's
Because
just
there have been freshenings in the past, we know of, that those have been recorded. But at least, but we didn't have enough observations yet, but in the oceans, but we had observations in the climate in Europe, and we didn't see anything in the climate in Europe.
So it's also not known how much of the polar cap should melt before it has an effect.
No, there is a big debate on that.
Right.
Yeah. So if it has to do with the rate of melting, because of course it won't jump in immediately. Okay. So it's more on that.
Yeah.
And if our present models, if they try to simulate what we have observed in the past, when there has been somewhat more melting, then those models say, oh, the climate in Europe changes. And we didn't see that. See? So it's very difficult. I mean, these climate models, I'm not a skeptical. Not at all. I do see that that we have had heating. But the predictions the range in the predictions is so much, between 2 and 6 degrees or 10 degrees. And that all has to do with uncertainties in that we don't know this system enough. I don't say we should not do anything, but in my view, only out of sustainability reasoning, you should do something. But whether it's heating up like 6 degrees or 2 degrees. I mean, I would say don't make the dikes now 2 meters higher. Let's really observe it and let's try to lower down the CO2 input, etc. And let's measure and see what happens. Or let's be more adaptive to changes, because also in a natural system, climate can change. But that does not mean I'm skeptical. Not at all.
I'm interested in the time frame. Suppose suddenly, I mean, I can imagine that there's somehow a threshold. If it doesn't sink anymore,
Yeah.
then it's not a matter of 100 years.
No. That's a big question. It's a big question. If you look at the geological studies and paleo studies, the more detailed they get, the faster the changes go. So it's really it's difficult to say.
Because this could happen in a couple of years. I mean, suddenly it stops and then...
No, well, yeah. It has happened in the past. Then we become Eskimos. No. Yeah, well, I mean, I can't say. We have now big programs in the North Atlantic measuring the overturning circulation and trying to see what kind of natural variability is in there, because there is also big debate. There seems to be a sort of 60 to 70 year variability in this natural variability in this system, like you have the El Nino, which is 6 to 7 years, which we know now because we started to study it 30 years ago and we have seen a few and now we understand it. But with a time scale of 60 to 70 years, we simply don't have data from 60 years ago. But computer models say that there could be a sort of natural variability in the whole system. So that makes this whole discussion very difficult, because the nature in itself also is variable on these timescales.
But anyhow, it's like warm weather. It's better for us that Antarctica melts than when Greenland melts, right?
Yeah, sure. Although when the vpro was with me a few weeks ago, I really on that day they phoned me from Radio 1 because there was a ANP news that on Antarctica there was a melting of, or there was a part of a big plate going down, and there was a serious news that this would influence the climate in Europe. It would we would have an ice age in Europe immediately. And then I looked to the background of this this news, and that was all much more relaxed. But it does show that we know that there is a global circulation in which all oceans are connected, and if you do something in one location, it can have effects somewhere else. That's true, but simply we don't know what the. It's always difficult to say you don't know, but it's reality in a few things. And to me, the El Nino is a very nice example, because 30 years ago, or when I came into this field, in the ocean field, which 15 years ago or so roughly, then they thought it's a 3 or 4 year phenomena, blah blah blah. But now we know it's not always the same. But we cannot predict it exactly. But what we can predict is 1 year ahead. If we know, oh, okay, now the ocean surface temperatures start to change, and then we can warn the farmers. Okay, take care. Next year, you should grow something different, because you will have a lot of rain. And if we think that similar systems are present at many more locations all over the world in our climate system.
Would we also put an enormous amount of salt in the sea?
Yeah. Yeah, well, that's a geoengineering approach. I'm with all these things on such a large scale, we really don't know. That's a difficult thing. If you don't know what's the effect of these large-scale things you do, like we do now with CO2. I mean, do we need to do something different to stop that, and then again something different because of other unknown effects we didn't know beforehand? It's much better to try to stop the sources of this all. I mean, in the end, we should have a sustainable thing. Use as much as the Earth gives in the same time frame. That's the end solution.
When you talk about the data, you just mentioned like 60, 70 years, probably a natural cycle. How old are actually those observations that you can trust? In other words, how old is your science?
Yeah, well, for the surface, it goes back, for the surface currents and temperatures on, it goes back to the VOC time, roughly. So there are projects at the moment now that they look at old ships' journals and get it again into the databases to be able to study far more in the past. But for instance, simply these moorings that we put out in the oceans now to measure the currents and the sea, that's only thing that we can do since 15 years or so. If we would not have GPS, we could not find them back. You cannot find them back with a sextant, because you have to be very nearby to pick them up again. So that's simply very recent stuff. And all those ideas on long-term variability come from mathematical models. And we know, I mean, if we compare, I won't show it, but if we compare our ocean observations with the ocean part of climate models, then it's bullshit. I mean, it's very bad. So I cannot believe these predictions so much, or maybe I believe that they are so wide. You see what I mean? And because they are so wide, it means that we don't know a lot of this system. It's ridiculous that one simulation gives you 2 degrees more, stated, and another simulation gives you, for the whole Earth, 7 degrees more. What to take? The average? Or no. But, I mean, all these things, there is development in this field. So, I mean, we can, gets better. But there are also parts we don't know which we simply cannot predict. I mean, we all agree, nobody has problems with the fact that I say to you, I cannot predict what the weather is in 2 weeks from now. Everybody agrees. How can we predict the climate in? I know, okay, but there are also, behind that there are reasons or sort of horizons of predictability. And then speak about the whole biological system, how that will respond to all kind of things. That's why we at NIOZ we measure everything in the sea, and then in biology, I mean, it's even much more difficult to predict all kind of things. Ja.
We zei in het begin van de simulatie van die ocean giants, die worden eigenlijk gereden.
Ja.